calorimetry, a science of measuring heat based on the change in temperature of an observed body when it releases or absorbs heat.
Heat capacity is defined as the amount of heat necessary to increase the temperature of a substance.
In this equation, the heat capacity is represented by a big letter C, the heat absorbed is represented by a big letter Q, and the change in temperature is represented by a delta and a big letter T. From this equation of heat capacity, an equation for Q can be derived. We can derive Q through this equation. We have to transpose the change in temperature through multiplying it by both sides. The derived formula is heat absorbed equals to heat capacity times change in temperature.
Specific heat is the heat capacity per gram of substance. It is equal to the heat capacity over the mass of substance.
This is the formula of specific heat. From equation C, we can derive another formula for the heat capacity. For us to get the formula of heat capacity, we have to transpose the mass of substance to both sides by multiplication. And this is the derived formula for the heat capacity. Basically, we just need to substitute the value of heat capacity in order to get this formula. The SI units for heat capacity, it is joules per degree Celsius. For specific heat, it's joules per grams degree Celsius. For heat transferred, it is joules.
Bomb calorimetry problem. When a 1 gram sample of the rocket fuel hydrazine N2H4 is burnt in a bomb calorimeter, which contains 1,200 grams of water, the temperature rises from 24.62 degrees Celsius to 28.16 degrees Celsius. If the heat capacity for the bomb is 840 joules per Celsius, calculate the absorbed heat of the reaction for combustion of a 1 gram sample. Also calculate the absorbed heat of the reaction for combustion of 1 mole of hydrazine in a bomb calorimeter. For the solution for a bomb calorimeter, use this equation.
Heat absorbed by reaction is equal to negative heat absorbed by water plus heat absorbed by bomb. In this case, negative 4.18 joules per grams times Celsius times mass. In this case, heat absorbed by reaction is equal to negative 4.18 joules per grams times Celsius times mass of water plus Celsius times the change of temperature. And heat, for the second problem, the same equation is used, where Q is heat flow, M is mass in grams, and delta T is the temperature change. Plugging in the values given in the problem, heat absorbed by reaction is equal to 4.18 joules per gram times Celsius times 1,200 grams plus 840 joules per Celsius times 3.54 Celsius. So the answer is negative 20,700 joules or negative 20.7 kilojoules. You now know that 20.7 kilojoules of heat is evolved for every gram of hydrazine that is burned. Using the periodic table to get atomic weights, calculate that 1 mole of hydrazine weighed 32.0 grams. Therefore, for the combustion of 1 mole of hydrazine, heat absorbed by reaction is equal to 32.0 times 20.7 kilojoules per grams, and heat absorbed by reaction is equal to negative 662 kilojoules. And the answer is negative 20 kilojoules and 662 kilojoules.
Heat absorbed by water is equal to 4.18 joules over gram Celsius multiplied to 110 multiplied to 26.6 Celsius minus 25 Celsius. And the total of heat absorbed by water is 550. Change of H is negative 550 joules. 0.010 mole H positive is equal to negative 550 joules. Therefore, for 1 mole of H positive or OH negative, the change of H is equal to 1 mole H positive multiplied to negative 550 joules over 0.010 mole H positive is equal to negative 55 kilojoules. The answer is 550 joules.
Calculate heat absorbed by water. Calculate the change of H for the reaction. Calculate the change of H if 1 mole of OH negative reacts within 1 mole of H positive. To solve this problem, use this equation. Heat absorbed is equal to specific heat multiplied by mass of substance multiplied by change in temperature, where Q in grams and change of temperature is the